Worlds in the Dark, a quiet sleep story about exoplanets and wandering worlds. The night sky often seems perfectly still, as though the whole universe has paused for the evening. On a clear night, far from the lights of streets and houses, the stars appear as tiny points scattered across a deep, open darkness. Some flicker as their light passes through the moving air above us. Others shine with a steadier glow. From where we stand, they seem almost unchanged. They watched over the first villages and the first cities. They guided travelers across deserts and oceans. They became calendars, stories, signs, and quiet companions. For most of human history, the stars were beautiful and unreachable. We could see them, name them, and wonder about them, but we could not know whether they had worlds of their own. We lived on our small blue planet, orbiting one ordinary star among hundreds of billions in the Milky Way. And we asked a simple question: is our sun the only star with a family of planets? Or is the darkness filled with other worlds? For a very long time, the answer remained hidden. Planets are small compared with stars. They are faint, and the light of their stars is overwhelming. Even a large planet can disappear in that glare, like a firefly drifting beside a distant lighthouse. Then in the early 1990s, the silence began to open. In 1992, astronomers confirmed planets around a pulsar, the dense remnant left behind after the death of a massive star. Those first known exoplanets circled a place stranger than anyone had expected. 3 years later, in 1995, Mitchell Mayer and Didier Queloz announced a planet around 51 Pegasi, a star somewhat like our Sunday. The planet was called 51 Pegasi b. It was a gas giant, roughly half the mass of Jupiter, completing an orbit in only a little more than 4 days. It traveled so close to its star that it was intensely hot, a kind of world that later became known as a hot Jupiter. It was not the first exoplanet ever confirmed, but it was the first confirmed around a sun-like star. And its discovery changed the way we imagine the sky. A star was no longer only a point of light. It could be the center of another system. It could have years, seasons, moons, rings, clouds, and landscapes that no eye had ever seen. By the middle of 2026, more than 6,300 exoplanets had been confirmed. Thousands more waited as candidates, requiring further observations before they could join the official count. The confirmed worlds are only a sample, a small collection gathered from an enormous galaxy. The evidence now suggests that planets are not rare exceptions. Across the Milky Way, there are probably more planets than stars. Some are enormous gas giants. Some are small and rocky. Some move so close to their stars that their surfaces may glow with molten stone. Others travel through colder outer regions, where water, methane, and other substances can freeze into ancient ice. There may be worlds rich in water, worlds wrapped in thick atmospheres, and worlds unlike anything in our solar system. We have not seen every shore or cloud. Often we know a planet only through a trace, a shadow, a gravitational pull, a faint warmth, or a brief bending of distant light. And yet from these small traces, whole worlds slowly emerge. Imagine looking toward one bright star. The star may be tens or hundreds of light years away. Its light has crossed space for years before reaching us. Beside it, a planet may be moving quietly along its orbit, but the planet is millions or billions of times fainter. Directly photographing such a world is possible in special cases, but it remains very difficult. The planets we can image most easily are usually young, large, warm, and far enough from their stars for their light to be separated from the glare. For most exoplanets, astronomers use indirect methods. They do not begin by looking for the planet itself. They look for what the planet does. One of the most successful methods begins with a shadow. It is called the transit method. If a planet's orbit happens to be aligned with our view, the planet will sometimes pass between us and its star. For a little while, it blocks a small part of the starlight. The star seems to dim. The change may be tiny. A large planet crossing a small star can make a noticeable dip. An Earth-sized planet crossing a sun-like star dims it by only a very small fraction. But sensitive instruments can measure that change. Then the star brightens again. After one orbit, the planet may cross once more. The same dip returns. Then it returns again, at regular intervals like a quiet clock hidden in the light. A repeating dimming is an important clue, but it is not always enough by itself. Star spots nearby stars and eclipsing stellar companions can imitate a transit. So astronomers compare observations, check the shape and timing of the dimming, and use other methods to confirm that a planet is truly there. From the depth of a transit, they can estimate the planet's size relative to its star. From the time between transits, they can measure the length of its year. From the gentle filtering of starlight through an atmosphere, they may even begin to identify gases high above the planet's clouds. A world can reveal itself by briefly standing in front of its sunday. But most planetary systems are not aligned for us to see a transit. Their planets pass above or below the face of the star from our point of view. For those systems, another method listens for a different rhythm. It listens for the wobble. A star pulls on its planets, but every planet also pulls on its star. The star is much more massive, so its motion is small, but it is not motionless. Star and planet orbit a shared center of mass, a balance point that astronomers call the barycenter. As the planet travels around, the star moves slightly toward us, then slightly away. When the star moves toward us, the dark and bright lines in its spectrum shift a little toward shorter, bluer wavelengths. When the star moves away, those lines shift toward longer, redder wavelengths. The star does not visibly flash blue and red. The change is far too subtle for our eyes, but a precise spectrograph can measure it. This is the radial velocity method. It reveals the planet's orbital rhythm and gives astronomers a lower limit on its mass. If the same planet also transits, its orbital tilt is known, and the mass can be measured more fully. Then size and mass can be considered together. Astronomers can estimate density and ask whether the planet is likely to be rocky, rich in water, or wrapped in deep layers of gas. A shadow gives one part of the story. A wobble gives another. And when the two are joined, the outline of a distant world becomes clearer. Most of the planets we know belong to stars. They move through repeating years, held in place by gravity. But some worlds appear to travel without a parent star. They are called rogue planets or free-floating planets. A rogue planet has no nearby sun to rise above its horizon. There is no bright local star to divide its sky into day and night. Instead, the stars of the galaxy would remain overhead, a faint and distant canopy. The word rogue can sound restless, but the motion itself may be calm. A free-floating planet still travels under gravity. It follows an orbit through the Milky Way, just as stars, gas clouds, and our own solar system do. How does a planet become free? Some may begin inside young planetary systems. A newborn system is busy with motion. Planets grow inside a disk of gas and dust. Their paths change as they pull on one another. They may exchange energy during close gravitational encounters. Sometimes, one world is sent onto a wider and wider orbit. If it gains enough speed, it can escape the gravity of its star. The departure may happen early, while the planetary system is still settling into its long-term shape. The planet then continues alone, carrying its moons, rings, atmosphere, and internal heat with it, if it had them and if they survive the journey. Not every isolated object must have been ejected. Some planetary mass objects may form directly from collapsing clouds of gas, in a process more like the birth of a star. Here, the language becomes uncertain. An object with the mass of a giant planet may be called a planet, a free-floating planetary mass object, or a very low-mass brown dwarf, depending partly on how it formed and on the definition being used. Nature does not always place a clear border where people would like to draw one. Some isolated objects may be failed stars. Some may be exiled planets. Some may have histories that are difficult to reconstruct. They all move through the same galaxy, and they may not be as cold as they first appear. A young gas giant can retain heat from its formation and glow in infrared light for millions of years. A rocky planet can carry heat from radioactive elements in its interior. A thick atmosphere can slow the escape of warmth. A deep layer of ice can insulate water below. Models suggest that, under certain conditions, a starless rocky world might keep a buried ocean liquid beneath ice, or perhaps maintain warmer regions beneath a very dense hydrogen atmosphere. This is a possibility from physics, not evidence that such an ocean has already been found. Still, it changes the picture. A world without sunlight need not be completely without energy. Under a dark sky, far below a frozen surface, heat may continue to move slowly through rock and water. The surface may be quiet. The interior may not be. Finding an isolated world is difficult. Without a nearby star, there may be no repeating transit and no stellar wobble to measure. An old, low-mass rogue planet may be too cold and faint to photograph directly. But gravity offers another way. It is called gravitational microlensing. Imagine a distant background star shining steadily toward Earth. Now imagine that another object passes almost directly between us and that star. The foreground object may be a star, a brown dwarf, a planet, or something else with mass. According to general relativity, mass curves space-time. Light from the background star follows that curved path. From Earth, the separate lensed images are usually too close together to resolve, but their combined light appears brighter. The background star slowly brightens. It reaches a peak. Then it fades back to its ordinary glow as the alignment passes. The lens may remain unseen. Its presence is written only in the changing light behind it. Microlensing events do not repeat on command. The stars and the lens continue moving, and the same alignment is unlikely to return. So observatories watch crowded fields near the center of the Milky Way, where enormous numbers of background stars provide many chances for alignment. Wide-field cameras measure millions of stars. Computer systems notice unusual changes. Teams compare data from different telescopes and different parts of Earth. Most microlensing events caused by stars last for days or weeks. A very low-mass lens creates a much shorter signal. For a free-floating planet, the brightening may last only a few hours, or perhaps a day or several days, depending on the planet's mass, distance, and motion. The briefest events are easy to miss. Clouds can pass over an observatory. Daylight can interrupt the view. A signal may begin and end between one observation and the next. That is why continuous coverage matters. Telescopes in different longitudes can pass the observation from night to night, following the darkness around Earth. Microlensing has revealed events consistent with isolated lenses, whose masses may be comparable to Neptune, Earth, or even smaller worlds. But the measurements can be difficult. A short event may come from a truly free-floating planet, or from a planet moving on a very wide orbit around a distant star. In many cases, the exact mass also depends on information that is hard to obtain from a single brightening. So astronomers speak carefully. They use words such as candidate, likely, and consistent with. This care does not make the discovery less beautiful. It shows how much can be learned from a moment of light, and how patiently each conclusion is built. Studies suggest that free-floating or very wide-orbit worlds may be extremely common. One recent estimate found that, across a broad range of masses, there could be many such objects for every star in the galaxy. The uncertainty is still large, and future surveys will test the estimate. For now, the honest answer is simple. There may be billions. There may be trillions. We do not yet know the true number. The darkness between the stars is not well counted. Some wandering worlds can also be found through their own faint heat. Young and massive free-floating objects are warm enough to emit infrared light. Their glow is invisible to human eyes, but infrared telescopes can detect it. The James Webb Space Telescope is especially sensitive to this light. Its primary mirror is made from 18 gold-coated beryllium segments. Its instruments observe wavelengths ranging from the red edge of visible light deep into the mid-infrared. Webb can study young planetary mass objects in nearby star-forming regions. It can separate atmospheric signals, measure temperatures, and detect molecules and changing cloud patterns in isolated objects that do not orbit a star. These objects are generally young, warm, and relatively massive. An old Earth-mass rogue planet would be far colder and much more difficult to see directly. For those worlds, microlensing remains the more promising path. Another observatory, NASA's Nancy Grace Roman Space Telescope, was built to watch wide areas of the sky with sharp infrared vision. Its planned survey toward the crowded center of the Milky Way will repeatedly measure vast numbers of stars. Roman is expected to discover many planets through microlensing, including planets in wide orbits and free-floating candidates with masses near that of Earth. Predictions vary with the assumed population, but studies suggest hundreds of Earth-mass wanderers and perhaps around 1,000 free-floating planets across a wider range of masses. The numbers are forecasts, not promises. The universe will decide what the telescope finds. That is part of the quiet beauty of astronomy. We build an instrument with careful hands. We send it above the atmosphere. We point it into a field of stars. And then we allow the light to answer. Now return, for a moment, to the open field beneath the night sky. The stars are still there. They seem as calm as they did before. But the meaning of the darkness has changed. A point of light may have planets moving around it. A slight dimming may be the shadow of a distant world. A tiny shift in a spectrum may be the pull of an unseen companion. A brief brightening may mark a solitary planet passing through the line of sight. A faint infrared glow may come from a world with no sun at all. The sky is not a simple ceiling of lights. It is depth upon depth, systems within systems, orbits crossing years that no human has counted. Somewhere a planet is passing in front of its star. Somewhere else, another star is moving gently around a barycenter. Far away, a young gas giant is cooling beneath layers of cloud. And between the stars, an unseen world is continuing along its path through the galaxy. None of these motions needs our attention tonight. They continue whether we watch or not. The telescopes can keep their patient vigil. The planets can keep their quiet rhythms. The stars can carry their light across the long distances. There is nothing to solve before morning, nothing to measure, nothing to hold in the mind. Only the thought of distant worlds turning slowly in the dark. Worlds with short years. Worlds with long winters. Worlds beneath red suns, white suns, and small, cool stars. Worlds with no sunrise at all, yet perhaps with warmth still hidden deep inside. The galaxy moves around them. They move with the galaxy. And above us, the night remains wide, quiet, and full of places we have only begun to imagine. You can let the details drift now. The numbers can fade. The names can soften. 51 Pegasi. A distant transit. A small spectral shift. A moment of lensed light. Then only the sky. And the slow, steady knowledge that the darkness is not empty. It is crossed by light. It is shaped by gravity. It carries stars, planets, and silent paths between them. For now, those paths can continue without us. The night is still. The worlds are moving. And there is time to rest.